Assalamualaikum and a very good morning. Okay, let's continue with the final part of the microstructure waveguide analysis. So we have discussed on the rectangular and circular, and in this slides or in this video, I'm going to discuss further about the planar waveguide analysis. Okay, so to refresh or to recap, so you can refer to the second video that includes a description on planar, strip line, and microstrip line waveguide. Alright, so this video consists of strip line and microstrip line planar transmission line analysis. So before that, please ensure that you scan the attendance QR code using UTM Smart. Okay, as has been discussed earlier, the strip line basically includes a flat strip of metal which is sandwiched between two parallel ground planes. So this is the microwave strip line. So if in comparison to the microstrip, so the microstrips where the conductor being placed on top. Okay, but for strip line, the metal strip is sandwiched, okay, in between two parallel ground planes. Alright, so the tables on the right hand side is basically some of the notation and also symbols that you are going to deal with in the strip line and microstrip line analysis. So to revise, the strip line supports TEM wave, TEM mode, and this is basically the common mode of operation for strip line. Okay, for strip line microstructure, so we can calculate the phase velocity for the TEM mode of operation, Vp, by using the following equation. So C is the speed of light and the epsilon R is the relative permittivity of the dielectric materials. Okay, in where the strip line is placed or being sandwiched in between two parallel metal ground plane, and the propagation constant beta is equivalent to the epsilon R, the square root of epsilon R k naught. So this one is k naught epsilon R. So epsilon R, again, the relative permittivity of the materials, and k naught is the wave number given by this equation, 2 pi f, the frequency of operation divided by the speed of light, and the wavelength of the line equal to lambda, while the characteristic impedance Z0 equal to 1 over Vp with the phase velocity multiplied by the speed of light, and the characteristic impedance can also be calculated by using this equation, in which it depends on the B or H, the thickness of the structure, B or H. Okay, and the WE here is basically the effective width of the center conductor. Okay, so effective width of the center conductor. Okay, why there is an effective width? Okay, because since the strip line lies in between two ground planes, so ground plane here, and you have the dielectric materials in between. Okay, due to the different properties of the materials that the strip line being exposed to, that's why we need the effective width. Okay, so the width here is W, so WE effective width due to the surrounding materials or some surrounding environment to the strip line. Okay, so the effective width can be calculated by using this equation, and B again is equal to H, the thickness of the overall structure. Okay, so for W over B larger than 0.35, so the ratio of the WE effective width divided by B equal to 0, and otherwise it will be this. Okay, alright, so when designing a strip line circuit, so the width is one of the important parameters that you need to look at. So we can estimate the W over B, the width, the ratio of the width to the height or the thickness of the structure by using this, in which it depends on the characteristic impedance and also the epsilon r, the relative permittivity of the structure. Alright, so if it is less than 120, so it will be equal to x, the ratio of the width to the height or the thickness equal to x, in which you can calculate the x equal to this equation. Okay, let's look at an example of a strip line. So a strip line has characteristic impedance of Z0 equal to 90, so Z0 equal to 90, and the length of 5 lambda over 8. Okay, so calculate the width and the length for the case of following substrates. Okay, so these are the general criteria of the strip line. So you need to calculate the width and the length for two different cases, which using different properties of substrate materials where the strip line is sandwiched. Okay, so in the calculation, use the F, the frequency equal to 5 GHz. Right, the answer is shown. However, as I mentioned earlier, you need to show clearly your steps, which include the general equation, and then include the values into the equation before your final answer. Okay, let's try this out. So the given question just now, you have the strip line with Z0 equal to 90 ohm and the length given as 5 lambda over 8. Okay, so and then you need to calculate the width and the length if the substrate used having these properties. Right, so to get the W and also the length, so refer to the equation, the related equation. So firstly, the one related to the width is basically from the ratio of W over B, in which it is equal to x 0.85 minus 0.6 minus x for Z0 epsilon r less than 120 ohm, or for Z0 epsilon r larger than 120 ohm. So to choose either W over B equal to x or the other one, so you need to calculate this one first, Z0 ER. Okay, so Z0 epsilon r, so your Z0 given is 90, and the epsilon r given for the first case is 5.23, so you get it equal to 205.82, so which is larger than 120 ohm. Therefore, you'll be using this. Okay, so your W over B will be equal to 0.85 minus 0.6 minus x. Then what is x? So x, you need to calculate from the equation of x equal to 30 pi divided by Z0 epsilon r minus 0.441. So 30 pi divided by Z0 is 90, epsilon r is 5.23 in this case. Minus 0.441. So in which your x should be equal to 0.017. So from here you can calculate the ratio of W over B equal to 0.85 minus 0.6 minus 0.017. So the ratio is 0.086. Okay, so now to get the W, so the W will be equal to 0.086 multiplied by your B, or the thickness of the structure. So you have two thickness in the question, where the thickness of the structure 2 mm or copper thickness. So B or H is equal to the thickness of the structure. The copper thickness is basically the thickness of the strip line. Okay, but I mean the metal strip. But for thickness, this thickness is basically for the whole structure. So in this case, 0.086 multiplied by 2 millimeter. So your W will be equal to 0.172 millimeter. Okay, so please be careful with the unit. If you want to use millimeter, so use millimeter for all calculation, or else you need to convert it into standard unit meter. Right, next you have the W. How about the L? So the L given from the question, okay, the L given as 5 lambda over 8, but what will be the actual value? So what is your lambda? So lambda equal to C over F. C is the speed of light divided by your F given just now is 5 gigahertz. So you can get your lambda equal to 0.026 meter. Okay, so then you can calculate your L equal to 5 lambda 0.026 meter divided by 8. Right, so you should get your L equal to 16 millimeter or 0.016 meter. Okay, so you already have your W and L. Alright, so same goes to the question B. So you need to use the suitable equation so that you can get the W and L. But this calculation only valid if there's no phase shift requirement in the structure. Okay, if there's phase shift requirement, so there will be additional equation that you need to consider. So I'll be discussing that in the Microstrip waveguide analysis. So for microstrip line analysis, so please make sure you know the difference between the structure itself, how the microstrip and the strip line looks like. Okay, so the strip line is sandwiched in between two ground plane, while the microstrips basically consist of a conducting strip separated from a ground plane by a dielectric material. So you have this metal strip, okay, and then separated by a dielectric or the substrate material, and you have another layer of ground plane at the bottom. Okay, but for strip line, the metal strip is in between two metal ground plane. Alright, so again the same parameters used in the analysis. So the phase velocity can be calculated by this one, and the beta is using the same equation, K naught epsilon effective. But for strip line just now, it's K naught epsilon R. Okay, so you need to be careful. So make sure when you refer to the appendix, you refer to the right equation, right? Okay, the slide shows some fabricated microstrip line that used as a coupler and also power divider. Okay, some equations involved in microstrip line analysis: the phase velocity as mentioned earlier, and the propagation constant beta equal to k naught, the wave number multiplied by the effective permittivity. In strip line, you use relative permittivity, the epsilon r, but in microstrip line, you use effective permittivity. Right, so the effective dielectric constant of the microstrip can be calculated by this equation, in which you have the d and also the width. The d is basically the height or the thickness of the substrate material that separate the microstrip line to the ground plane. Okay, the dielectric constant. Why we need to consider the effective dielectric constant epsilon e? Epsilon e, effective dielectric constant, because the dielectric constant of homogeneous material, okay, the effective, basically considering the homogeneous medium, replaces the air and also the region, the dielectric region of the microstrip. Okay, since this strip line is exposed to two different properties. The first one is the air and also to the dielectric materials. That's why, so that's relative permittivity for the substrate or dielectric materials, and you have another one, epsilon naught for the air. So from here you calculate the epsilon e, effective permittivity, where the microstrip line is exposed or is placed on, right? So then the wavelength of the line can be calculated by using lambda, still dependent on the epsilon e, the effective permittivity or dielectric constant. Okay, next is the characteristic impedance for microstrip line can be estimated by using the following equations, that it depends on the d, the thickness of the substrate, and the width. Okay, so and the ratio of the w to d can be estimated by using the following equations, where there's variable of a and b, which can be estimated by the following equation. All right, in the case of the line required to produce a phase delay of phi, okay, and the length of the microstrip can be calculated by this relation. Okay, the phi in radian, okay, equal to beta L. So beta is beta is the k naught, the wave number multiplied by the epsilon e square root multiplied by L, the length of the structure. Okay, so from here the k naught is equal to 2 pi f over c. So from here you can get dl, the length of the microstrip structure, considering the phase shift or phase delay required by the system. Okay. Besides equation and calculation, you can also estimate the ratio, the width and the height or the thickness of the substrate by using microstrip graph. So in which it's basically show the relation between the Z0 and also the ratio of W over H. So once you know the characteristic impedance, for example 100, then you can estimate what will be the ratio of W over H by knowing the constant, okay, the epsilon, relative permittivity of the substrate material. Okay, for example, if the substrate material used is 2.3, so and the Z0 or characteristic impedance equal to 100. So this is the line for 2.3, crossing there, so you can actually get the ratio of W over H is about 0.9 something. Okay, the ratio of W over H. Okay, same goes to you can estimate the wavelength, or you can estimate the W over H if you know the wavelength of the structure and you know the epsilon r of the structure as well. So the wavelength of the microstrip or the design basically is the relation between the lambda g and lambda naught. Lambda g is the microstrip, the group wavelength, divided by epsilon naught is the free space wavelength. Okay, and in practical, there will be some losses, okay, due to the property of the dielectric materials where the microstrip metal is placed on, and also the surrounding environment. So there are two common losses in microstrip transmission line, which are the dielectric and also the conductor losses, which can be estimated. So D for dielectric, when you can estimate the losses by using this equation. So you have the wave number, relative permittivity, effective permittivity, or dielectric constant, the loss tangent, and also okay, that's it. All right, same goes to the conductor loss. C for conductor loss, alpha is the attenuation or the loss, where it relates the RS, the surface resistivity of the conductor, okay, in which you can estimate by using this equation and divided by the characteristic impedance and also the width of the structure. Okay, the dielectric loss, as I mentioned, due to the fields around the microstrip line itself, okay, which where the strip line is exposed to the air and also to the substrate material or dielectric materials, which are lossy materials. Okay, let's look at an example on microstrip transmission line. So given the microstrip that has characteristic impedance Z0 equal to 120 ohm, so Z0 equal to 120 ohm, and it with a 90-degree phase shift. So you have the phi equal to 90 degree at the F equal to 2.5 gigahertz. Determine its width and length, so the W and the L for the cases of the following. Okay, now again you have two different substrate materials. So I think the steps are more or less the same as the strip line. However, in here you need to consider the phase shift. Okay, the line is required to produce a phase shift of 90 degree. Right, therefore you can calculate the L by considering the phase shift. Okay, the phase shift equal to beta L. So in which is L, beta is K0 epsilon R, epsilon E in this case. So since it is microstrip, so you can get the epsilon E from the by using the equation, and then K0 is the wave number equal to 2 pi F over C. Okay, what else? Okay, don't forget the phase will be in radian. Okay, from here you can get the length, and the width, as usual, you can get the ratio of W over H. Then you can get the W, the width of the structure. Okay, for earlier example, you can also estimate. You can also compare your calculation with the graph. Okay. So you can refer to the Z0 versus W over H. So you can compare your W over H value with the one you have calculated. All right, so another example given for a strip line or microstrip line, it can be both. All right, so you need to calculate the width again, the L, and what happened when you change the characteristic impedance equal to other values. Okay, the first one is 50 ohm. What happened when we change it to 20 and 70? Right? So you can compare the values and put it in a table. I'll share the table at the end of the video. Right, this is just the some revision on the cycles, the wave. Okay, how about the phase shift and etc. Okay, this is the answer for the additional exercise just now. So you need to perform the calculation before you refer to this table, and you can see the difference between the strip line and the microstrip line parameters when you change the characteristic impedance. Right, this is the main reference for this topic. Thank you.